Good morning. We're going to talk about AsyncIO and music. My name is Łukasz. I come from the internet. You can find me in all sorts of places online. I used to live in Poznan, then I moved. Now I moved back, so I can hang out with you guys if you'd like. I actually used to work at STX Next like a decade ago, so nice to be back. But today we're going to discover how AsyncIO can be used to process MIDI to drive hardware synthesizers. And because we are serious people, we're going to do it live, so we can possibly do it wrong. I'm Łukasz. I build synthesizers. This is my setup at home that I'm very proud of, but it doesn't lend itself very well to moving it. So today I have something else for you. I brought an Ovation circuit, which is a standalone music proof box. It's production grade. If you are into electronic music, Aphex Twin is using a lot of Ovation hardware, so it is actually used in actual performances. We'll be using this circuit as a drum machine today. In fact, here it is. It runs on a battery. It's like a standalone music studio that you don't need a computer for. So in fact, what we're going to do today is not going to involve much in terms of computing. You're going to see that in a minute. I also have with me a circuit monostation, which is a monophonic analog bass synthesizer, which we're going to use to drive the bass sound here. So, drum and bass then. And then we are going to hear sounds because they go through our own mixer. That mixer is hardware, which means all sounds we're going to hear today are hardware driven by those three devices. They don't go through a computer at all. They're going to be sequenced by Python. So before we begin, let's talk a few minutes about AsyncIO. I don't really have much time, so let's teach you AsyncIO in 5 minutes. Should be easy, right? Oh, but the most important slide is already up. If you understand that AsyncIO is essentially an event loop that calls Python functions one after the other, you understand the most important thing about AsyncIO. This is what it is. It's an event loop. It has a list of functions to run, and based on certain rules, it just runs those functions one after the other. Done. How do you actually run the event loop? Easy peasy. You just get it and run forever. In fact, if you look inside, since Python is open source and we can see, this is literally a loop, right? So the event loop is actually a loop that just runs once, and then as long as we don't stop it somehow, it just continues to do so. So what can it run? An event loop can call functions, and you can actually make those functions runnable by scheduling them on the event loop by call later or call soon. Call later says wait at least this many seconds. Call soon means as soon as you're free, as soon as you're done with things that you're already running at this time, run my thing. So you can schedule stuff like this, and it's gonna work at runtime somehow like the graph on the right shows you. However, really, it's kind of, what is not maybe obvious at first is that because it really runs functions one by one, what happens is if a function is time consuming, if it has an action that takes a long time, then all the following actions have to wait for it. If they have to wait, that means it just slows everything down. So that doesn't actually achieve any concurrency, and probably if you've heard about AsyncIO, you heard about it in the context of being able to do many things at once in one Python thread. So how is this achieved? Well, instead of using blocking functions like the callback that we have now, we're using coroutines. We're using async functions, right? And instead of just using regular blocking calls, we're using asynchronous calls that we're awaiting on. So how does that work? We're gonna see this in a minute. Let me just tell you that here, those three awaits that we see here still essentially mean that those things run one after the other. So there's no concurrency yet, but what you can do with coroutines that we have, you can gather it. So if you call it like this, with AsyncIO gather, now it tells AsyncIO, hey please, run those things concurrently. It doesn't run them in parallel, it doesn't use multiple threads, it doesn't use multiple cores, but run them concurrently. But wait, how can it run those coroutines concurrently if it's literally an event loop that just calls functions one by one? Well, it is essentially a very easy trick that AsyncIO is using, which is called a trample. What it does is, if you are creating coroutines like here, what Python does internally is it's creating a task. And that task, at the end of its init method, is just scheduling itself on the event loop. But it just schedules a single step. So what is a single step? If you look at the function, again, in the AsyncIO source code, you're going to see that it really runs the coroutine to the next await, and then gives the control back to AsyncIO, so it can select a different coroutine for a while, and then that different coroutine does exactly the same, runs until the next await, and gives control back to AsyncIO, and so on and so on. So with this kind of round robin, what we achieve is the illusion of parallelism, but which is concurrency. So we don't do like active blocking, active waiting on things. We are using our single thread to the max. So in graphical form, that would look something like this. You're going to have this coroutine 1 that runs its step, then coroutine 2 that runs its step, coroutine 3 that runs its step, and then round robin, because as soon as this step was done, it scheduled itself again on the event loop, and so on until we're done. So now you know AsyncIO. You're welcome. Music. Before we get to MIDI, if you are not into music, you probably don't know musical notation, you probably don't really know much about those things, don't worry about this. The only thing that you need to know for this particular talk is that there are notes. Those notes just happen to map certain frequencies, and you can see like piano keys. If you press a piano key, it just plays a certain frequency. In musical notation, those are kind of like this. What is important for us here is that there are 2 bars of music, and each of those notes is actually not a whole note, it's a quarter note. What does that mean? Well, it just takes a quarter of a bar. So whatever tempo we set to be playing, that is the quarter of an entire bar of music. And then you have notes which have certain frequencies. And 4 by 4 just means we're just going to have 4 quarters into a single note here. So that's it for musical notation. MIDI, what's that? MIDI is one of the few protocols in any industry really that is absolutely widely adopted and allows hardware of different manufacturers, of different vendors to talk to each other. Like, it is actually one of the most prevalent protocols in musical hardware. Essentially every hardware that is production grade is going to support MIDI. Historically, it used to use those DIN sockets, those DIN plugs, which were like regular analog plugs that were unidirectional, which means that a single cable only sent information one way, right? Like, that was the historical thing, but those cables were flimsy and kind of rather cumbersome to use. So these days, there's USB MIDI instead, which is bidirectional, but it's the same kind of thing. It's the same protocol on the wire. And what is that protocol? That protocol is actually like endearingly simple. It is just a stream of messages that tell you that, oh, on a particular channel, you should start playing a note with a certain velocity, and after a while, you might want to stop playing it. And again, play a note and stop playing that note. There's different channels, because if you wanted to have a piece of hardware that can support multiple sounds at the same time, it would be very frustrating to have a cable for each of those sounds. So there's 16 channels that MIDI is supporting on one connection. But essentially, this is it. This is how it literally looks on the wire. There's a command saying on a given channel, play a note, and after a while, stop playing a note. It's synchronous, meaning as soon as that information gets on the other side, it should be executed. There's no wait, there's no scheduling for things to happen later on. It's just that. So wait, if you have a bunch of hardware, we have 2 pieces of equipment here, how come can they stay in sync and play together? Well, MIDI also sends a lot of packets like these. They're just clock packets. It actually sends 24 pulses per quarter note. We learned already about what quarter notes are. So it sends a lot of them. But that's enough of a resolution for a human to just perceive that, yeah, it's very good in sync. It's kind of, it just sounds like it's perfectly synced in parallel. It's great. So what we're going to do next is we're going to be playing those hardware synthesizers with Python. We're going to be sequencing those with Python. But we're going to actually tell Python how fast it should play by using one of those instruments' clock signal. So we're going to be using the clock that is on the circuit to control how fast Python is going to sequence things, and it's going to play those. So we're going to have drums, and we're going to have some bass sounds. Before we get to the demo, though, I wanted to show you the main function of what we're going to deal with, because it fits on a slide, so I guess it might relax you a bit that it is actually something that we can draw. So, first of all, our async main function just gets the MIDI ports out of our operating system. I did connect both devices with USB MIDI, so the operating system sees them under certain names. So circuit, our drum machine, circuit monostation are bass, right? So we're going to have those two ports that we're getting. As soon as we have them, we can create a queue for messages, for MIDI messages. We are getting the AsyncIO event loop, and then what we're going to tell Python is, hey, every time a MIDI event is happening, we're getting a MIDI event, can you please run this function? This function is so small that I just kind of pulled it inside of the async main, also because we are using that loop right here, which is a closure. But anyway, like, we are just using that callback right here every time there is any MIDI packet coming in. We're not going to be actually using that MIDI packets from the monostation, just from the circuit, so let's close that port, so there's no queues that are going to be filling up. And then, this is going to be something I'm going to show you in a second. There's a performance object. It's essentially a data class. We just need to store some state, so why not in a dedicated object? We're just going to run forever a consumer of those MIDI messages that came on a queue. We have them on a queue, so we can now have an asynchronous function that is going to decide what to do with them. Finally, after we cancel it, meaning Control-C, we are done with our program, we're essentially done. We don't have to do much, like all the asynchronous stuff is going to cancel neatly on its own. The only thing that we have to do is we have to cancel the callback that we scheduled, because behind our backs, the MIDI library that we're using is using a C++ thread that actually every time a MIDI message comes through is running our Python function. If we shut down AsyncIO but still kept the callback running, what will happen is Python will be very unhappy that we are calling things on a closed event loop. So we're saying, hey, cancel that callback. Single line of code is easy. But obviously the most interesting thing is happening in that line, like MIDI consumer. What does that do? It also fits on a slide, so I guess that's easy. It's essentially a loop. And that loop is deciding what to do with incoming messages on a queue. So either it's a clock, in which case we're just going to measure how long it was since the last clock. That is the simplest thing that we can do for now at the start to see how fast we should be going. And then what we're going to do is, if we get a start signal, we're going to create a task on AsyncIO to start our drum machine. If we're getting a stop signal, we're just going to cancel that task and we're going to just delete it, right? So simple enough, but what that enables us to do is, if our program is running, we can start and stop the performance anytime we want. So this is actually production graded, it syncs with hardware, pretty cool. So obviously that task, that drum machine is going to be the first thing that we're going to do live now. But I don't have slides for it anymore because we're actually going to just do it programming, like, in an editor, seeing this in practice. So again, what we're going to do is we're going to have hardware playing for us by sequencing it with Python. Okay, let's see how it works. Alright, so that's the drum machine. Can you see the code clearly, or should I get it a bit bigger? Good. A bit bigger? No, not that. Fine. Boom. How about now?
Very
cool. So if that works for you, it works for me as well. This looks unbelievably simple, right? I mean, it cannot just be a loop that just plays a drum every 24 pulses. What is happening? Is that really it? Well, yes, it is. There is a little complexity hiding here, but as you can see, the complexity is seriously just kind of encapsulating things that we want to do, right? So the way we're playing on an instrument is in fact just sending MIDI messages. So we're sending a message to play a note on, then we are waiting for a given time, and then we're telling it to stop playing, right, after this time. So that's the only thing that is actually happening here. There's no magic. It's literally that. So that our drum machine for the time being is just that. It's just going to play a drum every 24 pulses, but as we know, pulses go per quarter note, so you can pretty much expect how this is going to sound. Let's try it out. Okay, we need to start. 4 to the floor. We can start a party right now. That's a bit boring though, right? So let's do things. And now we're gonna need 2 hands, so I hope you're gonna be able to hear me. Okay, so we have the bass drum right here. What if we actually also added a snare drum right after it? Snare drum, again, 24. That is going to sound just a bit more interesting. Again, it starts, and now we have this bass, right? A bit more interesting. But what if we actually used those hi-hats? Flykate is very unhappy about those two being here, but not being used. So let's make Flykate happy. To do this now, it seems like we would like the hi-hats to play at the same time. But we are already awaiting, we already have a loop. What could we do here? What if we actually encapsulated this in this way? We can say that there's an async depth, which is a bass drum. That bass drum is going to be that. Cool. And now we're going to have another one, that is the snare drum. Cool. But we have to loop it over it, and for it to play every second note, what we should actually do is we should just let it wait for those 24 pulses and then play. But now we just have a bunch of async depths. How do we actually make them run? Well, we make them run by awaiting on AsyncIO gather, right? So we can gather the bass drum, and we can gather the snare drum. Well, I promised you hi-hats, so let's do something easy. Async depth hi-hats. Hi-hats are percussion, so they're gonna be like something like this. Let's play the hi-hat, play drum. The drum is gonna be closed hi-hat twice, let's say 6. And now for 12 we're gonna play the opener. We need to add those 2. And that's essentially it. It still fits with this huge font on a single screen. Let's hear whether this is any good. Pretty good. However, if you really hear closely, they're not exactly the same. Something is off. And if you actually change the tempo, you can hear that they're going out of sync quite terribly now. That's not what we wanted. Like, something is not quite right. What is happening? What is happening here is when we were gathering our information on how quick the clock signals are coming from the synthesizer, what we were doing is we're just measuring the time like between 2 clock signals. But then we weren't synchronizing that in any way. What happened was the bass drum was playing and waiting on its own accord with some particular weight. The snare drum did this exactly the same, and it was waiting on its own accord. And the hi-hats were waiting on its own accord, but there was never a moment where they would synchronize. This is actually a problem that even production hardware has. And that problem even has a wiki page. It's called clock drift. If you have a clock and everybody is getting that clock, but they're never synchronizing when we should actually play, things are going to go out of sync and they're going to sound rather terrible. So what we can do is fix that by introducing some form of synchronization, and this is where AsyncIO shines. What we should do is we should just make a bunch of small edits here, but for me to be able to show you and not make too many typos, let's just see how the diff looks like. So first of all, let's check out the thing, and let's see where we are. Full drums, this is where we are, and let's see what the diff with the next thing would be. So see, instead of just sleeping naively for the number of pulses that we wanted to wait for, what we're going to do now is we're going to wait on some magic metronome object. We're going to see how it works in a second. And to have this work, we're just going to, instead of, oh, I actually do the thing the opposite way, so let's, yes, exactly that. So we're gonna be, instead of gathering the delta, we're gonna just tick every time we get a clock message and reset whenever we start. So there's a metronome. How does that work? Fortunately, it's rather easy for us to see that in practice. The metronome is just a very, very small class that uses an AsyncIO feature for synchronization. What does that mean? AsyncIO works on coroutines, like you've seen how they work, but it also is based, like internally, on futures. Futures are very simple Python objects that literally tell you this. At some point in the future, I'm going to have a result for it. I don't have it yet. I will have it in the future. So what we actually have to do, we just have to set a future that just counts the pulses that we want to wait for, and finally we're going to have a result, which means we don't have to wait anymore. And that waiting for a metronome for the number of pulses is literally achieving this. So if you see the diff on this side, the wait is really means just run await this wait on the metronome. And the wait on the metronome seriously just means let's create a countdown and just await on that. And that countdown is seriously an AsyncIO feature that we can set some particular context on, which is how many times we want to wait for it, like so how many pulses we want to wait for it. So after those are done, AsyncIO can proceed. So is that any better? Does that sound any better? Let's try it out. Better than some of the production hardware that you pay real money for, because we will always be staying in sync. But I promised you bass, and there's no bass yet, so let's fix that. Actually, again, let me just show you a diff, because it is deceivingly simple. To add the bassline in our MIDI consumer, the only thing that we have to do is, whenever we're starting, we're also going to be creating a task for the analog synth. And when we are stopping, we're just going to say, hey, please, don't play anymore. The only thing that we're also doing is we're saying, you know what, can we also have all notes off? The reason why is that if we stopped at a wrong moment where a note on signal was sent, it would just keep playing that long note forever. It would annoy the hell out of you. So instead, we're just telling it when we're pressing stop, please stop playing whatever you're playing. And the analog synth, again, looks exactly as complicated as the drum machine did. So let's get there. I can check out this for basic bassline. Boom, here it is. How does it sound? It'll probably sound kind of weird because it just plays a single note over and over again. That note is just C2. It's playing it with a certain velocity, so of course, like it can be either louder or quieter, and we set the K. What does that mean? Well, if you actually play a piano, right, or a trumpet, you never play for the entire length of a note that you have in your sheet, right? Like if you're playing a trumpet, you have to breathe. If you're playing the piano, you have to actually change the position of your hands, so there's always some kind of tiny fragment of the note that you're not playing, it's silent. But here we're just saying, let's play for the exact right amount of the note, because it's just mechanical hardware. Like, it doesn't have to take its hands from the keyboard. So this is what the decay means. 1.0 means play for 100% of the note, which by default it wasn't. Here is already quite okay. We can play with the filter that we have on the hardware, which kind of sounds nice and whatnot. However, it's very boring to just a single note. So let's actually do some sequencing. To do some sequencing here, I could type this again, but in the interest of my own embarrassment from making typos in front of you, let me just show you this. That's an arpeggiator. Again, you should recognize that we just created the same thing as an internal async function, and now we have an arpeggiator. What does the arpeggiator do? Well, we're taking 3 separate notes, and we're cycling through them with iter tools, because anything that you're going to do in Python that is non-trivial is going to import iter tools. Happens every time. So you have an iter tool cycle, and we're just randomly choosing a length of the note, an octave like that we're going to play in, and that particular note, and you're just playing. Well, I told you this is a monophonic synthesizer. It's kind of weird, like how can we play 2 things in unison? In fact, it's just how you would press a single note and play other notes on top of it. What the monophonic synthesizer will do is it's going to do a particular like nice kind of synthesis that sometimes does like glides between frequencies or whatnot. Depends on what you do with all those notes. But it turns out you can actually press multiple notes at the same time on a keyboard, even if your synthesizer is monophonic. So let's see how this is. I didn't really write any of that, and that's just using very, very simple Python to generate sequences for it. Which is pretty interesting on its own. I like it because if you see the tempo is still the same as your hardware, you can make it faster, you can make it slower. But can we actually perform with this? Can we do something that's going to react to the stuff that I'm doing? Well, we can. The simplest thing that we can do here is we can make this recognize notes that I'm playing on the keyboard of the circuit, right? Like, which is going to show you that like we're playing on this drum machine's keyboard, but it's actually going to impact sound here. So check that out. I want to show you the bit because it is CD percent. Look, we're just going to record the last note that the circuit saw me pressing, right? Which is literally what we're doing here. Like when we're getting a note on, let's just record it. And then we're going to, instead of just saying C2 every time, we're going to use it for this the bass note of the bass note. So now I can actually check out this. Ooh. So the change is very minimal, but it allows us to actually do much more interesting music. I'm sorry for that, but like I literally see like a very alarming red 5, 4, 3. Like seriously, it's like on a MacGyver episode. So I'm gonna be here for an entire day. So if you have any questions about AsyncIO, about Python, which is Release 3.8, you should use it. Or any of those toys that I love a lot, just come and ask. Thank you.